In this video, we're going to talk about graphing exponential functions. An exponential function is a function in which the independent variable x is in the exponent rather than the base of the exponent. When dealing with an exponential function, it's important to know what the base of the exponent is. So let's consider the function y equals 2 to the exponent x. We can make a table of values using the x values of -3, -2, -1, 0, 1, 2, and 3. And if we do that, we get the y values shown: 1/8, 1/4, 1/2, 1, 2, 4, and 8. So what we're going to do is graph a curve that has all of those points. And if we plot the x and y axis, you see them there. And if we plot the points themselves, you see them in red. And so if we actually connect them all, hopefully it's kind of clear here, we'll get a curve that looks something like this. It'll go infinitely in this direction. It'll never actually touch that horizontal x-axis because 2 to the exponent x, even if we have a number like -1 million for x, we're still going to have 1 over 2 quantity to the exponent 1 million. And although that'll be a very small number, it'll never actually equal 0. So the line y equals 0 will be a horizontal asymptote. It'll be a value that the curve itself gets infinitely close to but never actually touches. Okay, now the curve will look like that. We have an arrow on each end, and we'll see that the horizontal asymptote will be at y equals 0. There will be a y-intercept right here at 0, 1. The domain will be all x element of the reals. And the range will be any y that's an element of the reals so long as y is greater than 0. Okay, and we don't forget to put an arrow on each end. Now, what if we have the function y equals 3 to the exponent x? Again, we can make a very similar table of values. And when we plot all those points, we'll get a curve that looks very similar. It'll actually be a little steeper this time, but it'll have some similarities in the way it behaves. We're not going to forget our arrow on each end. We'll be able to say that we have a horizontal asymptote at y equals 0, a y-intercept again at x equals 1. And just to reiterate, that's because it's the function y equals 3 to the x. So if x equals 0, then y equals 3 to the 0, and any value to the exponent 0 is going to equal 1, except 0 to the 0, which is undefined. We have a domain of x being all real numbers, and we have a range of y being all real numbers so long as y is greater than 0. Okay, we don't forget to put an arrow on each end. Now, what if we have the function y equals 1/2 to the exponent x? Well, just to show you, 1/2 to the exponent -3 is the same as 2 over 1 to the exponent +3, which is 2 over 3, which is 8. What ends up happening is we actually have the same values in our y column that we had when we did 2 to the x, but they're in the opposite order. So we get points like this, and after we plot those points and draw a graph to the best of our abilities, it looks something like that. And we have a horizontal asymptote at y equals 0, a y-intercept at 0, 1, a domain of all real numbers, a range of all real numbers greater than 0, and we put an arrow on each end. And if we have the function y equals 1/3 to the x, a similar drama occurs. The y values for y equals 3 to the x and 1/3 to the x are the same. They're just in opposite orders. So when we plot all those points and draw that curve, it looks like this. We have a horizontal asymptote at y equals 0, a y-intercept at 0, 1, a domain of all real numbers, and a range of all real numbers greater than 0. And we can't forget to put an arrow on each end. And so what we recognize is there are certain commonalities of all the exponential parent functions. Even if we did 5 to the x or 1/12 to the x, it wouldn't even matter. They all have certain similar characteristics. There's going to be a horizontal asymptote at y equals 0, i.e. the x-axis. There will be a y-intercept at 0, 1. The domain will be all real numbers, and the range will be all real numbers so long as y is greater than 0. Now, what if we were going to deal with transformations involving exponential functions? Well, what you want to do now, we're going to graph a more complicated exponential function, but what you want to do is remember a few things. First, you're going to want to determine the base of the exponent. And so for purposes of the further discussion here, we'll say the base of the exponent is b. Now, you're going to want to determine 3 key points that go through the mapping formula. And the 3 key points, if the base of the exponent is b, we'll use the parent function y equals b to the x. And so we'll use points where the x is -1 or 0 or 1. So if our parent function is y equals b to the x and x equals 1, then y will equal b to the 1, or in other words, b. Assuming b doesn't equal 0, of course, then if we have an x value of 0, then b to the 0 will equal 1, and b to the -1 will be 1 over b. Okay, and that's what we have listed here. Our 3 key points will be 1, 1 over b, or in other words, b to the exponent -1, as well as 0, 1, and 1b. Now, there will always be a horizontal asymptote at y equals c. And the reason for that is that the parent function has an asymptote at y equals 0. What we're then going to do is put the value of y equals 0 through the second half of the mapping formula. We remember the mapping formula from previous units, and the mapping formula always says that xy will map onto x over k plus d and ay plus c. So looking at the second half of that, we'll see that y will map onto ay plus c. Well, since the y value of the asymptote is 0, 0 will map onto a times 0 plus c. A times 0 is just 0, so in other words, 0 will map onto c. And so the horizontal asymptote originally at y equals 0 will become a horizontal asymptote at y equals c. Now, the input of an exponential function is in the exponent. So the exponent needs to be k bracket x minus d. We've seen in previous units when we used the transformation mapping formula that the input was always k bracket x minus d. Since that's in the exponent, that's where we put it. So putting all this together means we're going to have, after we figure out the base of our exponent, the base of our exponential function, and call it b, we're going to have y equals a times b to the exponent k times x minus d plus c. And recall that sometimes these values aren't valid, so just like in previous sections, if you don't see, or sorry, I didn't mean to say these values aren't valid, I meant to say not visible. If you see that one of the, if one of the values isn't seen by you, then the a value is 1, the k value is 1, the d value is 0, and the c value is 0. Those are what I sometimes call the default values. And we've been through all that in previous units. So what if we wanted to graph the function y equals 1 minus 3 times 2 to the exponent 1/2 x plus 2? Okay, well, what we could do right away is say the base of my exponent is 2. The exponent is 1/2 x plus 2, but I'll call it x plus 4. I'm multiplying that by -3, and then this 1 is simply something I'm adding on the end. So this is really what y equals. Okay, so points on that parent function y equals 2 to the x will be the points shown that I've just circled. And after doing a little rearranging, we'll get this expression right here. So if a equals -3, k equals 1/2, d equals -4, and c equals 1, because that's what you get an a value of -3, a k value of 1/2, a d value of -4, and a c value of 1. If you're wondering what's happening with the 2, what's interesting about this parent function is that that 2 is informing what specific points go here. But after we know those specific points, we don't involve the 2 in any more of our mapping formula dealings. So we take each one of those points, -1, 1/2, 0, 1, and 1, 2, put them through the mapping formula with these values that we said earlier. And when we do that, we get outputted the points -6, -1/2, -4, -2, and -2, -5, with a horizontal asymptote at y equals 1, because that horizontal asymptote's always at y equals c. So since that horizontal asymptote's always at y equals c, y equals c is right here. Y equals 1 is right there. We see that our domain will be y less than 1. Now, this a value of -3 means that we'll have a reflection in the x-axis as well as a vertical stretch by a factor of 3. That k value of 1/2 means we'll have a horizontal stretch by a factor of 2. The d value of -4 means we'll have a translation to the left 4 units, and that c value of 1 means we'll have a translation up 1 unit.